You talking about me?
No.
Are you sure?
Where did you find the value for mercury? Like the
For here?
R, yeah, the R.
Oh, it's on. It should be on your sheet, on your blue sheet. Yep. So the R values are given. They're in the.
The millimeters of mercury is not on.
Yeah, it is. Well, it's in torr, but torr is the same as millimeters of mercury. If you look right below there, it says 1 ATM equals 760 millimeters of mercury equals 760 torr.
Yeah.
So torr and millimeters of mercury are the same thing. So that would be 62 point. I use 0.4. They have 62.36. It comes out. By the time you do sig figs, it's going to give you the same answer. Okay, so that's where I got that 62.4. Good? All right. Then we shall put that to bed and do our kinetic molecular theory. So, kinetic molecular theory essentially has several, they call it postulates here, but ideas behind it. Size of the gas particle is so small compared to the distances between them that the volume of the particles is negligible. So that's to say that it is so small that the volume of the gas particles can be ignored. Gas particles are in constant random motions. They move in straight lines until they bump into the walls of a container. It's kind of like if you've ever played billiards or pool and you hit the pool ball, it's going to move in a straight line until it hits the side of the table. When the particles bump into the walls of the container, that is what causes your gas pressure. The particles are assumed to have no attractive or repulsive forces. So in effect, they have no IMFs. When they have no IMFs, those are called ideal gases. Now, in reality, they do, but if we can ignore those IMFs and work with ideal gases, it makes our life much easier. So luckily in this course, that's what they choose to do.
Not an organic.
The average kinetic energy of a sample, then, of a gas is proportional to the Kelvin temperature. And then the kinetic energy equals 1/2 mv squared, mass and velocity squared. So kinetic energy is equal to 1/2 times the mass times the velocity squared. This is physicsy stuff. We're dipping our toe in the physics pond, y'all. All right. Here are some relationships that you need to kind of wrap your head around. Boyle's law, pressure and volume. So P1V1 equals P2V2. This is inverse. So if one goes up, the other goes down. This is volume of the container. So you have to kind of wrap your brain around the difference between volume of your container and number of moles. So number of moles is the amount of gas you have in there. And people oftentimes think of that as the volume. It's not. Okay, number of moles is different. So if I'm blowing up the balloon, the volume of the balloon is getting bigger. And as I add more moles of gas, I'm adding more moles in as well. But the volume, I can change that, right? So I can tie off the balloon, and then I can change the volume of that balloon. I can compress that gas up, to a point until the balloon pops. But I can change the volume of that balloon then. But the amount of gas in there would still be set because it's tied off. All right, Charles's law then does a direct relationship. If the volume goes, or if the temperature goes up, the volume goes up. Gay-Lussac is temperature and pressure. So if the temperature goes up, the pressure goes up. And then you can combine those into a combined gas law. Maxwell Boltzmann, this will be on your test in some form. It always shows up inevitably every year, okay? It's going to show you the distribution of the kinetic energies of the particles at a given temperature. And you can see that it skews to the right. The tail of the right is longer as the origin speed is 0. Speed can't be less than 0. You can't go less than 0. So Maxwell Boltzmann distribution shows the kinetic energies at given temperatures. And if you look at it, you can kind of see here, as we go up here, it's going to move this way. You're going to have more, and a hot gas, you're going to have more particles that are moving at a faster speed than if you're at room temperature or if you're colder. So colder gases are going to move slower. By increasing the temperature, you're going to skew it more this direction. So if you are looking at one of these distributions and you want to know the most probable speed and they've got values off to the side, the peak is going to be your most probable speed in that sample. The average speed then would be about right here. In here, you can tell that the temperature of this gas is higher than the temperature of this gas. What is different about the two drawings? Yep. So you need to be kind of getting used to that. Here, you can see that this one is bigger particle than this one, okay? But, and then you can kind of see that this one's going to be moving a little bit faster than this one. It's going to have more kinetic energy anyway. All right, calculating the formula for kinetic energy, it's kinetic energy equals 1/2 mv squared. Mass and velocity are counted on in here. The mass is the mass of particles in kilograms, and the velocity is in meters per second. So the rate of the energy is then calculated in joules, and you can calculate the rate of a fusion through a small hole. So remember, a fusion is diffusion through a tiny hole. So like a puncture in your tire would be an example of that. And it says that the rate 1 over rate 2 equals the square root of the molar mass of 2 over 1. And if you think of that, you know, that's your velocity and your mass. So you can see as the particle size increases, the rate of diffusion, effusion, is going to decrease. So the bigger the particle, the slower it's going to lose that gas out of there. All right. Given these samples at the same temperature, place the particles in order of decreasing average particle speed. So which one will go faster will go first, and which one goes slower will go last. So which one's going to go the fastest? H2 will go the fastest. Which one's going to go the next? HCl, and then followed by Cl2. The size, yep. They're at the same temperature. So then the size is what's going to play the part in that. All right, if we have equal molar mixture of gases, hydrogen, nitrogen, fluorine, placed in a container with a pen-sized hole opening, that means it's going to go through a fusion. After some time has passed, place the gases in order of increasing amount remaining in the container. So which will you have more of? Which will you have the least? What you thinking? Which one are you going to have the least in that container? Which one's going to get out more? H2 is going to get out more, so that's going to be the least remaining. And then what? N2 followed by F2. And this goes by molar masses. So the molar mass of this is 2 the molar grams per mole. The molar mass for this guy is 28 grams per mole, and the molar mass of this guy is 38 grams per mole. So he's going to move slower. Okay? It's like me running around a track versus some skinny thing running around a track. I'm going to take longer. There's a lot of factors in that too. But we'll just talk about weight right now. All right. The next part is deviation from ideal gas law. So, like I said, our calculations are pretty much always going to be assuming that we are using the ideal gas law and that we're working with gases that are ideal, but they want you to think about gases that aren't. So they're not going to make you do calculations with these because they don't give you the math to do that with. But they want you to think about why this and in what conditions a deviation from the ideal gas law would occur. Okay. So, like I said, kinetic molecular theory is going to assume that we're under high temp and low pressure. So think about high temp and low pressure, and think about low temp and or high temp and no, I'm sorry, low temp and high pressure. So the reason why gases act ideally is because they have no IMFs. Okay, so those are the intermolecular forces. If the thing starts moving slower, then it's going to have more of a chance for those IMFs to take hold because they're going to get closer together. Okay, it's kind of like if you're running around the track and you're running a relay. When they're running a relay, they have to slow down a little bit before they do that baton handoff, right? They're not running full speed at the transition point. Am I correct?
That's ideal if you are.
It would be ideal if you are, but that can't happen in reality. I mean, it's just not going to work very well, right? You have a much higher chance of bumbling that and dropping it, and then you got a real problem. So they have to slow down a little bit. So when they slow down, they have a chance of hooking up. It's the same idea here. If these are going slower at a lower temperature, then they have a chance for those IMFs to take hold. And then high pressure makes sense too, because if you're pushing those molecules together under high pressure, they have a chance of getting together and forming IMFs. So those are the conditions where you're going to end up having gases act less ideally. Okay, which would be low temp, moving slower, and high pressure. They act more ideally under high pressure because they're moving so fast around, they can't hook up. And then over low pressure, because they're just further apart. They're not pushed together. Okay, so volume in terms of ideal gas law equation is the volume of the container. It assumes that the volume of the particles within the container is negligible. So that's to say that the volume of the particles taking up the container is so small that it can be ignored. Again, at low pressures and, the volumes are so small that compared to that of the container, we ignore that. At high pressures, the molecules occupy a significant part of that volume of the container, and therefore that's why they're going to act less ideally. So gases under high pressure and low temp end up acting less ideally because, like I said, they're going to be able to kind of clump together more and have those intermolecular forces take hold. So at 10 atm, we have a 100 Kelvin sample of radon. It's going to deviate from its predicted volume based on the ideal gas law. If radon has a smaller volume than predicted, propose an explanation to justify that observation. So why, if it has a small volume than predicted, why would this start to deviate from the ideal gas law? Yeah, it's getting closer together, and so therefore, it's going to act less ideally. If radon has a larger volume than predicted, what are you going to see? Is it going to act more like an ideal gas or less? More, because the particles are further apart. All right. So here we've got two samples, sample 1 and sample 2. They're both at 298 Kelvin. Identify the gas that is more likely to deviate from the ideal situation. So which one would I deviate? The second one, because
Close together.
yeah, they're closer together. You've got more particles in there, so there's chances of them kind of hooking up and there's IMFs taking hold. All right. So that is all I am doing today. You guys have time to work on homework if you'd like.